the previous lecture, we have started our discussion on optimization methods to solve unconstrained optimization problems. In particular, we have discussed the steepest descent method, and also we got to know the convergence of the steepest descent method in the previous lecture. We have seen that the steepest descent method has the global convergence property, but it is a slow method. It has a linear rate of convergence. Now in this lecture we will discuss one of the fastest known optimization algorithm to solve an unconstrained optimization problem, that is the Newton method. However, we shall see that although this Newton method is one of the fastest known method, but it has a local convergence property. It does not converge globally. And in this lecture we will neatly discuss the following topics. Agenda of this lecture are three topics. First, the derivation of the Newton method, and after deriving the Newton's method we will find that there are several drawbacks of the Newton method, although it has a fast rate of convergence. So after deriving the Newton's method we will try to identify its convergence rate. We will find that Newton's method has a local convergence. That means if we start the method from a point that is very nearby to a local minimizer, then the method rapidly converges to the local minimizer. And after this local convergence, we shall try to see the scaling effect on the Newton's method. That means if we transform the variable space to some other variable space, from the space of x to, let's suppose, x hat given by some transformation matrix t times small x, then whether the Newton's method gets changed from the space of x to the space of x hat, that we shall try to see. Finally, to alleviate some drawbacks of the Newton method, we will try to identify a few modifications of the Newton method. Those are at first the damped Newton method, and then the Levenberg-Marquardt technique will be described. Let's start. At first, I will describe the derivation of the Newton method. Recall that the method of steepest descent uses only the first order partial derivatives, that is the gradient of the function, in selecting a suitable search direction. This strategy is not always the most effective, that we have already seen, that if we just go with the negative gradient direction, then the method is terribly slow. It has a linear rate of convergence, and therefore the strategy of the steepest descent method is not most effective. If however we use the higher order derivatives, the resulting iterative algorithm may perform better than the steepest descent method, because the higher order derivatives, like the second order derivative, that captures the curvature information of the function, and therefore it is expected that if we include in our iterative process the information of the second order derivative or the Hessian matrix, then the method may perform better than that of the steepest descent method. Newton's method is one of such methods. This Newton method is sometimes also called the Newton-Raphson method, and it uses first and second derivatives, and indeed it does perform better than the steepest descent method if the initial point is close to the minimizer. The idea behind this Newton method is as follows, that given a starting point, we construct a quadratic approximation to the objective function that matches the first and second derivative values at that point. That means, hypothetically, let us suppose if the graph of the function or the surface of a function of two variables is, let's suppose, this function, that is the objective function of the minimization problem at our hand, for which we wanted to identify a local minimizer. So let's suppose this is the graph of the function of two variables x1, x2. To find a minimizer or a minimum point of this function, what we do is as follows, that if we are at the kth iterative point, as let's suppose this point xk, and let's suppose at this point xk, the corresponding point to xk on the objective function is, let's suppose, this point. Now at this point we try to approximate the surface of the function z equals to f x1 x2 by a quadratic approximation. We consider here a Taylor's quadratic approximation around the point xk by, say, this quadratic function that passes through this point on the surface. So this particular point is a point on this quadratic approximation, say qx1 x2, and also a point on the surface of z equals to fx1 x2. And here this quadratic approximation is such a quadratic function that matches the first and the second derivatives with the function f at the point xk. So we can use here evidently the quadratic approximation q as a Taylor's quadratic approximation. Now after considering this quadratic approximation q of the function f at the point xk, the next iterative point is taken as the minimizer of the function q. So we consider the point that corresponds to the minimum value of the function q. That is, let's suppose this point. At this point we have the minimizer of the function q. This point is the next iterative point of the process. So we consider this point as the next iterative point xk plus 1 of the Newton's method. So what we do here is that we start our derivation with assuming a function of n variables that is twice continuously differentiable, and let's suppose we intend to find a local minimizer of this function f. To find a local minimizer, we start our process with a given initial point, say x0, and then to find the next iterative point after the general kth iterate, say xk, we consider Taylor's quadratic approximation about the point xk. We consider the Taylor's quadratic approximation because then the approximated function q and the objective function f will have identical gradient and Hessian. So first and second order partial derivatives of q and f will be identical, so that the approximated function q will carry the curvature information of the function f. So we consider Taylor's quadratic approximation about xk that will yield the function fx approximately equal to fxk plus gradient of f at xk times x minus xk plus half x minus xk transpose, the Hessian of the function f at the point xk times the vector x minus xk. This approximate equation is valid around the point xk. So we let this approximated function as qkx, and then we find a minimizer of the function qkx to identify the next iterative point xk plus 1. So we consider the next iterative point xk plus 1 as the argument vector that minimizes the function qkx. Now to find a formula for this xk plus 1, we go for finding a solution of the equation qkx is equal to 0, because this is first order necessary optimality condition for the function qk. Then at the point xk plus 1, we certainly have gradient of qk at xk plus 1 is equal to 0, which gives gradient of fxk plus Hessian of f at xk times the vector xk plus 1 minus xk, that is equal to the null vector. So this yields the point xk plus 1 is given by xk minus the inverse of the Hessian at the point xk times the gradient of f at xk, provided this inverse exists. So we got an iterative or recursive formula to identify the sequence of iterative points xk's. This recursive formula is referred to as recursion relation in the Newton's method, or it is also called full Newton method. And we refer this step xk plus 1 minus xk is equal to inverse of the Hessian at the point xk times gradient of fxk as full Newton step. And this we write as pure Newton method. So in pure Newton method, what we see here is that from the current iterative point xk, we move along the direction of negative Hessian inverse times the gradient of the function f at the point xk. And along this direction, say dk, we take one unit step and reach at the point xk plus 1. And as here no line search is performed to appropriately identify the value of alpha k, we refer it as the pure Newton method. So in the pure Newton method, the process is as follows, that you start your iteration from a given initial point x naught, then at the point x naught you identify the Newton direction d naught given by the Hessian inverse at the point x naught times the gradient at x naught. Then after identifying this d naught, you find the next iterative point x1 as x naught plus d, and then at x1 you find the gradient of the function and check whether the gradient of the function at the point x1 is below a tolerance level say epsilon. If yes, then you return x1 as a minimizer or a stationary point of the function f. But if this is not less than epsilon, then you go for computing the next iterative point x2, for which we need to find d1 at the point x1, and then x2 is given by x1 plus d1, and then you go for checking whether the gradient of the function f at the point x2 is having norm less than epsilon or not. If yes, then you stop, otherwise keep doing this process iteratively unless and until you find a point xk at which the gradient has norm less than epsilon. So this is what exactly the process in the pure Newton method. We refer it as pure Newton method because we are using this pure Newton direction without bothering about the step length, and we are adding this direction in the current iterative point to find the next iterative point. Now here in the pure Newton recursive formula, we notice that we have assumed the Hessian is invertible at the point xk, and therefore Hessian should have inverse across all the points in the iterative sequence xk. But this might not always be the case, that across all the points xk's, the inverse of the Hessian exists. In addition to these drawbacks, there are a few more serious issues of the pure Newton recursive formula. Those are as follows. The first is that the inverse of the Hessian at the current iterative point xk may fail to exist. And then in this case the method breaks down, and this will typically happen when, for example, in the regions where the objective function f is linear. And towards the end of this lecture, we will go with the derivation of the Levenberg-Marquardt modification, in which we shall see how to alleviate this drawback of the pure Newton method. The next serious drawback of the Newton method is that we are deliberately using this direction dk as the direction of movement from the point xk to reach at the point xk plus 1. But we are not really bothering whether this dk is a descent direction or not. And it might be possible that this direction dk along which we move in the pure Newton method may not be a descent direction. So we write it here that the direction dk may possibly not a descent direction, and therefore the pure form of the Newton method may not be a descent method. That is, possibly we may have that if xk plus 1 is not less than f at xk. Here you may think that in case this direction dk is a descent direction, then the pure Newton method may be a descent method. But unfortunately, you see that we are not bothering about the step length also here. We are deliberately using the step length as the unit step length. And this unit step length may possibly give us the next iterative point xk plus 1 as such a point for which the function value is bigger than equals to the function value at xk. So even if this pure Newton direction dk is a descent direction, unit step size may not yield the point xk plus 1 with f xk plus 1 less than f xk. Here, this method is not having a descent property in optimization is really a serious issue. But fortunately, it is possible to modify this pure Newton method such that this descent property hold. We will shortly have a modification called damped Newton method, in which we shall see how to choose a step length for which you will have this descent property. The next drawback of the pure Newton method is that this pure form of the Newton method tends to be attracted by the local maxima just as much as it is attracted by local minimum, because it just tries to solve grad f is equal to 0. And this drawback is eventually not only for Newton's method, this drawback is for every descent method that we shall describe throughout this course. But this drawback is not a frustrating drawback, because we have seen that for a descent method, an iterative sequence xk generated by a descent method never converges to a strict local maximum, and there are current researches on how to escape from saddle points. And we have also got to know that any descent method in optimization almost always converges to a local minimizer. So this drawback is not a frustrating drawback. But another drawback of the Newton's method is that execution of the inverse of the Hessian, especially when the number of variables in the objective function is huge. Because you notice that this Hessian matrix is a matrix of order n by n, where n is the number of variables. So if n is large, this inverse computation of the Hessian is really very tricky, and it requires quite a bit of computational cost. To alleviate this computational cost of the inverse of the Hessian, so for large n, what we do is as follows, that we look at the derivation of the Newton's method, and we see that the next iterative point xk plus 1 is given by this equation, and this equation can be written as a system of linear equations. You denote this direction as dk, and then we see that this dk is given by this xk plus 1 minus xk is known. So if we somehow get to know what is dk, then we will be able to identify what is xk plus 1. Now to find dk, what we do, we go for solving this system of linear equations. You notice that this entire expression is equivalently obtained by solving this system for y, that Hessian at xk times y is equal to negative of the gradient of f at xk. So you go for finding a solution y for this system, and that y is nothing but dk. So you go with this y to find xk plus 1 given by xk plus y. Now to solve this system, what we do is we seek the help of the Cholesky factorization. And the Cholesky factorization for this system is computed as follows. So for large n, we can apply Cholesky factorization on solving the system of linear equations Hessian at xk times y is equal to negative of the gradient at xk, and then consider the point xk plus 1 is equal to xk plus y. And if you find y by solving this system of linear equations, you notice that you don't require to compute inverse of the Hessian matrix at the point xk. Now to solve this system of linear equations, what we do is that if this Hessian matrix is positive definite, then we all know that there exists a unique Cholesky factorization, that we can write this Hessian matrix by L transpose, where L is a lower triangular matrix. Then you plug this expression LLT over here, and we can solve this system, say star, by breaking into two parts, that the original system is LL transpose y is equal to the negative gradient, which can be solved by first considering that, let's suppose this is some other variable z. So you solve this system, Lz is equal to negative of the gradient, and then finding a solution z for this system of linear equations. You go for solving L transpose y is equal to z, and then you find what is an expression for y, and this y will give us a solution to this system star. And we notice that this y will then give us the next iterative point xk plus 1, and in this process of applying Cholesky factorization alleviates the computation of the inverse of the Hessian. But what if this Hessian matrix is not positive definite? In this case, what we do is we tactfully increase the diagonal entries of the Hessian matrix. We add each and every diagonal entry by some significant amount, say the constant mu k. So we revise this Hessian matrix by the Hessian plus mu k times the identity matrix of order n. And for a significantly large value of mu, we notice that this matrix is a positive definite matrix. Then after revising this Hessian matrix by this matrix, we employ the Cholesky factorization, and this process of adding mu k in with the Hessian is known as the Levenberg-Marquardt modification of the Newton method, which we will detail towards the end of this lecture. Now we will look at the Newton's method from a different perspective. As a special note, I would like to mention that Newton method can be thought of as steepest descent method with respect to a matrix norm. I put the observation as a note that the Newton method is a solution to the following optimization problem, with the variable of the optimization as is given by xk plus 1 minus the generic variable x of the original problem. The pertaining optimization problem is minimization of the gradient times the vector s subject to the norm of s with respect to the Hessian matrix, which we refer as ellipsoidal norm, is less than equal to 1, where this ellipsoidal norm is given by positive square root of S transpose HKS. Here this HK is the Hessian matrix of the function f at xk, and we are assuming this HK is a positive definite matrix. Then only the Newton method is well defined, that the inverse of the Hessian can be computed, and the pure Newton direction dk is a descent direction. So we assume here that this HK is a positive definite matrix. Provided this HK is a positive definite matrix, we can show that this pure Newton method is a solution to this optimization problem. So we assume here that this HK is a positive definite matrix. Here this norm of S with respect to HK is known as ellipsoidal norm, because if we go for graphing out the curves for norm S HK is equal to some positive constant. Let's suppose you go for drawing for some constant, let's suppose 1 or 1.5 or 2 or whatsoever positive you take, you will find that this norm is equal to some positive constant will give us elliptical curves, and thus this norm is called as ellipsoidal norm. We notice here that if we replace this HK by the identity matrix of order n, then this ellipsoidal norm reduces to the usual Euclidean norm. Now, why this Newton method is a solution to this optimization problem? To find an answer to this question, why Newton method is a solution to this optimization problem, we seek the help of an inequality for ellipsoidal norm that states that for any two vectors, say x and y in Rn, we have the absolute value of x transpose y is less than equal to norm of x with respect to a positive definite matrix capital A and norm of y with respect to the inverse of this positive definite matrix A. And here the equality in this inequality happens when the vectors x and A inverse y are linearly dependent. Here this matrix capital A is a symmetric and positive definite matrix. Now we go for employing this inequality to solve this optimization problem, because this HK is a positive definite symmetric matrix. So what we can have is that for the objective function GK transpose S, where this GK is the gradient of the function f at xk, we have its absolute value is less than equal to the norm of S with respect to the Hessian matrix HK times norm of GK with respect to the inverse of the Hessian matrix. And equality occurs when the vector S is parallel to the inverse of the Hessian times the gradient. That is, when the vector S is given by some constant multiplication of this Hessian inverse gk. In particular, you choose this constant vector to be -1. So with this -1, we see that S is equal to hk inverse gk into -1 is nothing but the pure Newton direction. And therefore, the pure Newton direction is a solution to these minimization problems. And hence, the pure Newton method is a solution to this optimization problem with respect to the ellipsoidal norm for the matrix Hk, the Hessian matrix of F at the point xk. Now here, as we know that with respect to the L2 norm, the usual Euclidean norm, we all know that a steepest descent method is a solution to this minimization problem gk transpose S subject to norm is less than equal to 1. Here this norm is the usual Euclidean norm or Levenberg-Marquardt norm. As the steepest descent method is a solution to this optimization problem, and with this hk is equal to the identity matrix, this ellipsoidal norm reduces to the Levenberg-Marquardt norm. Newton's method is also called steepest descent method with the hk norm or the ellipsoidal norm. And here we notice that at each and every iteration of Newton's method, this ellipsoidal norm gets changed because hk gets changed, and hence the Newton's method is also called variable metric method, because at each and every iteration we are changing the norm or the metric being used to solve this minimization problem. So here we neatly write that Newton's method is a kind of steepest descent method with the ellipsoidal norm or hk norm, as at each and every iteration the norm gets changed because hk gets changed. The Newton method is also called a variable metric method. But the steepest descent method is not a variable metric method, because in steepest descent method we notice that the norm being used here is not a variable metric, that across each iterations we are going to use this norm, the Levenberg-Marquardt norm, not like here this hk norm where at each and every iteration hk gets changed. So after all these notes, then we go next to alleviate the drawbacks of this pure Newton method. We start with the first drawback. For the first drawback, I have already mentioned that if the inverse does not exist, then you go for revising this Hessian matrix by Hessian plus mu k times in, which is called the Levenberg-Marquardt modification. And this Levenberg-Marquardt modification will alleviate this drawback of the Newton's method. Now, for alleviating the next drawback, that the pure Newton method is not a descent method, what we do is that instead of using the unit step size, we consider a step length alpha k given by the exact line search or one of the inexact line searches, and then we can see that when this Hessian matrix is positive definite and thus the inverse will exist and this direction is a descent direction, then in that case, by using the step length with the help of exact or one of the inexact line searches, will yield a revised Newton method called a damped Newton method that is having this descency property. So we write out here that in order to alleviate the drawback of the Newton method not being a descent method, what we do is we take the help of the following result that states that let the sequence xk be the sequence generated by the Newton's method. Here, this notation C2 is the set of functions that have continuous second order partial derivatives. Now here in this result, if the Hessian at xk is positive definite and the gradient of the function at xk is not a null vector, then the pure Newton direction dk is equal to negative of the Hessian, its inverse times the gradient, is a descent direction for the function f at the point xk. This result is, although very trivial to realize, it is just straightly followed from the dot product of the gradient and the direction dk that gives us negative gradient transpose Hessian times the gradient, and this expression is negative because the Hessian matrix is assumed to be positive definite. And by this observation that the dot product of the direction dk and the gradient has negative value, then obviously the direction dk is a descent direction. Once this is a descent direction, then this result motivates the following modification of the Newton's method. That along this direction dk, you go for employing exact line search or inexact line search. Accordingly, take the step length alpha k, which will then give us the next iterative point xk plus 1 that has function value less than fxk. We write it here that the above result motivates the following modification of the Newton method, that you take xk plus 1 to be given by xk minus alpha k times the direction dk, that is given by Hessian inverse times gradient, where this alpha k is given by the exact line search along the direction dk, where dk is this negative times this Hessian inverse into gradient, or you choose this alpha k to be given by one of the inexact line searches. Then we see that as this direction dk is a descent direction, provided this Hessian is positive definite, then at the point xk plus 1 you will have the function value lesser than the function value at xk. So with this choice of alpha k, or you choose alpha k to be given by one of the inexact line searches, and then you will find that this modified Newton method has the descent property, provided the Hessian is positive definite and the gradient is not a null vector. That is, you will realize that the function value at xk plus 1 is less than the function value at xk. This modified Newton method is known as damped Newton method. This modification of the Newton method is due to alleviating the second drawback of the Newton method, that we have had this drawback that this pure Newton method does not have descency property. Now for the next drawback, this drawback I have already mentioned that this drawback is not a very crucial drawback, and this drawback is even for every descent method. For the next drawback, that evaluation of inverse Hessian requires high computational cost. I have already mentioned that we can employ the Cholesky factorization. So now next we will go to checking if the Newton method is having the quadratic termination property. That is, let us go for checking whether the Newton method terminates within n iterations, providing a minimizer of a quadratic function of n variables that has positive definite Hessian. That is, you consider the objective function fx as having the expression half times x transpose qx plus b transpose x plus c, a quadratic function where this capital Q is a matrix of order n by n, a positive definite matrix, b is a vector in n dimension, c is a real number. Now we go for employing the Newton's method on this quadratic function, and let us check whether the Newton method terminates within n steps. Now, as per the derivation of the Newton method, it is really evident that the pure Newton method reaches a minimizer or a minimum point of this function with just one step, because we took a quadratic approximation of the function f to find the next iterative point in the Newton's method. As this function f itself is a quadratic function, so obviously the next iterative point is the exact minimizer of this function f. We neatly prove this result, the quadratic termination property for the Newton method. We neatly write that as per the derivation of the Newton's method, the method for the function fx where q is a positive definite matrix reaches the point x bar with grad f x bar is equal to 0 in just one step, starting from any arbitrary initial point x naught in the n-dimensional Euclidean space. Here this matrix Q is a positive definite matrix, as well as we assume that it is a symmetric matrix. Now to see that this Newton method reaches a global minimizer of this function f in just one step, we calculate the next iterative point x1, that is given by x naught minus the Hessian inverse times the gradient, and that gives us x naught minus the Hessian matrix of this function f is the matrix Q, so Q inverse times the gradient of f at x naught, that is given by Q x naught plus b. So this gives us x naught minus Q inverse b, which is equal to the point x bar, where this x bar is a solution to grad f x bar is equal to 0, that is q x bar plus b is equal to 0. So x bar is given by minus q inverse b. That is what we have gotten this point x1. And therefore the Newton's method reaches at a global minimizer or a stationary point of a quadratic function with positive definite Hessian in just one step. And hence the Newton method has a quadratic termination property. Well, for a quadratic function, then Newton's method reaches the minimizer within one step. But what about for a general function? We shall next jump on deriving the convergence result of the Newton method. But before this convergence result, let me now quickly go through the scaling effect on the iterative formula of the Newton's method. In finding whether the Newton method is affected by the scaling effect, What we do, we consider a transformation of the variable space from the space of x to say x hat, where x hat is given by Tx, where T is a transformation matrix which is pre-assumed to be invertible. Then in the transform space, the space of x hat variables, we compute the Newton's iterate xk plus 1 hat for a given xk hat. After computing this xk plus 1 hat, we go for acting the T inverse on this xk plus 1 hat and check whether the xk plus 1 in the original variable space is identical with this T inverse xk plus 1 hat or not. Now in finding whether this xk plus 1 is going to be identical with T inverse xk plus 1 hat or not, we go for computing the gradient, Hessian, and then the Newton direction, and afterwards this xk plus 1 hat in the x hat space. To find this xk plus 1 hat, then we see that if we are having the objective function as fx in the x space, and suppose in the transformed variable space x hat, the objective function fx is reduced to f hat x hat, that is given by fx, or in terms of x hat it is f of t inverse x hat. Now we compute the gradient in the x space, gradient with respect to the variable x, and we go for computing the gradient in the x hat space with respect to x hat. We all know this gradient in the x hat space is given by, in terms of the gradient of the function f, as T inverse transpose grad x fx. Next, the Hessian. The Hessian in the x hat space, we all know, is given by T inverse transpose the Hessian in the x space times T inverse. We have computed this relationship and this relationship in detail in one of the previous lectures. Now we go for computing the Newton's direction, which is negative of the Hessian inverse times grad fx in the x space, and the Newton's direction in the x hat space is given by the Hessian inverse times gradient of f hat at x hat. These in terms of the Hessian and gradient in the space of x is given by minus t times the Hessian inverse times the gradient. This expression can be found just by plugging of this expression and this expression over this Newton direction. Now we go for computing xk plus 1 hat in the x hat space, that is given by xk hat minus the Newton direction at xk hat in the x hat space, which in turn, by plugging of this expression, is equal to xk hat minus t times the Hessian inverse at the point xk times the gradient at xk with respect to x. Now by employing t inverse on both the sides, what we get is this t inverse xk plus 1 hat, that is nothing but xk plus 1, and t inverse xk hat gives us xk minus This T inverse times T gives us identity matrix, and this second term then yields the Newton direction in the X space. And therefore what we get is that you compute xk plus 1 hat in the x hat space, and then by applying T inverse, the inverse transformation of this transformation x hat is equal to Tx, you will obtain the point xk plus 1 in the original variable space. So by transformation of variables or by scaling of variables, the Newton method is unaltered, and thus Newton method is called scaling invariance or affine invariance. We notice that for an invertible transformation matrix T, this transformation Tx is a linear transformation, which is a particular case of affine transformation, and thus Newton method is also called affine invariance. So if the calculation is easy in the x hat space, you go for computing Newton's iteration in the x hat space and then apply the inverse transformation to obtain the sequence of iterates in the original variable space, the space of x. Now next I will give you a home task, that here I have shown that Newton method is scaling invariance or affine invariance. But if we go for a change of the dimension or a scale of the objective function f by, let's suppose, the original objective function is fx, and we scale up it by say some constant multiplication of the function fx, we obtain a new function phi x. Now you go for computing the sequence of iterates xk given by the Newton's method for the function phi x, and go for computing the sequence of iterates for the function fx. Now the question is, are these sequence of iterates xk for f and xk for psi x are identical if we employ the Newton's method? So here neatly the question is the Newton method scale independent for the dependent variable, say z? We have seen that scaling of the variables xs will not alter the sequence of iterates. Is this true for scaling of the objective function or the dependent variable z? I put this question as a home task because the answer to this question is a bit easy to identify. So I am keeping as a home task, you please try to identify. Or precisely you try to identify for which values of c's this constant c, the Newton method is scaling independent of the dependent variable z. Now we will jump to the convergence analysis of the Newton method. Now in finding the convergence analysis of the Newton's method, we say that an iterative algorithm is globally convergent if for any arbitrary starting point x naught, the algorithm is guaranteed to generate a sequence of iterates xk that converges to a point x bar that satisfies the first order necessary condition of optimality, that x bar is such a point for which gradient of fx bar is equal to 0. Obviously here we are assuming that the function f is a differentiable function. Then the first order necessary optimality condition is given by this gradient of f is equal to 0. Now it is not always the case that every iterative algorithm in optimization is having a global convergence. But when an algorithm is not globally convergent, it may still generate a sequence that converges to a point satisfying the first order necessary optimality condition, provided the initial point is sufficiently close to the point x bar. We define here the term locally convergent first, that when an algorithm is not globally convergent, it may still generate a sequence that converges to a point satisfying first order necessary optimality condition, provided the initial point is sufficiently close to the point x bar that satisfies first order necessary optimality condition. In this case, we say that the algorithm is locally convergent. Now, with a quick inspection of the Newton's method through a geometrical interpretation of the Newton's iteration, we can quickly identify that the Newton's method do not have global convergence property. For simplicity of the explanation, let us consider that we are given a function of one variable that is known to have continuous second order derivatives. Now, if we employ the Newton's iterate for this function f, then the iterative formula for this function f gives us xk plus 1 is equal to xk minus f dash xk divided by f double dash xk. And this iterate is aiming to find a point that satisfies the first order necessary optimality condition. That is, simply it aims to find a solution to this equation f dash x is equal to 0. And if we define a function, a new function gx, which is given by the derivative of the function f, then we notice that this sequence of iterates xk aims to find a solution for gx is equal to 0. Here, in terms of the function g, this iterative formula reduces to xk plus 1 is equal to xk minus gxk divided by g dash xk, which in turn is the equation 0 minus gxk divided by xk plus 1 minus xk is equal to g dash xk. That is, we notice that the point xk plus 1 is a 0 of the function given by the equation y minus gxk divided by x minus xk is equal to g dash xk, which we notice that is the equation of tangent on the graph of the function gx at the point xk. So xk plus 1 is the point of intersection of the x-axis and this tangent at the point xk on the graph of the function g. Now we consider a very typical graph. Let's suppose the graph of the function gx is let's suppose a kind of this graph. Y is equal to gx, and we notice that for this function gx, a root of the equation gx is equal to 0 is this origin, that is x is equal to 0. Now if we start the Newton's iteration from a point, say over here, a bit away from the point x is equal to 0, then the next iterative point is given by the point of intersection of the tangent on the graph of gx at the point x is 0, that is this line. Then the next iterative point is given by the point of intersection of this tangent line and the x-axis. So the next iterative point x1 is over here. Then for the next iterative point x2, we need to consider the tangent On the graph of the function at this point, so we consider the tangent at the point x1, and we will obtain the next iterative point x2 is over here. Then at x2 we go for identifying the tangent, then take the point of intersection of the tangent with the x-axis. You will get the next iterative point x3 and so on. So what we get here is that the locations of these iterative points x0, x1, x2, x3 are such that they are subsequently getting away and away from the exact root x is equal to 0. And hence for this function gx, the Newton iterates xk is a divergent sequence. This is due to the fact that the point xk is chosen bit away from the point x is equal to 0. If however we would have chosen the initial iterate close enough to the solution x is equal to 0, then we notice that for this initial point, the next iterative point is given by the point of intersection of the tangent with the x-axis, this point x1. At x1 then we go for drawing the tangent, and that gives us the next iterative point over here, and then at x2 you draw the tangent. So here the subsequent points x0, x1, x2, x3 and so on, they are getting closer, closer and closer to the point x is equal to 0. That is the solution of gx is equal to 0. So if we choose x0, the initial point, close enough to a root of gx is equal to 0, then Newton iterates get converged. But if we take x0 a bit away from a solution of gx is equal to 0, then the Newton's iterate xk may not be a convergent sequence. And therefore Newton's method do not have the global convergence property, because for different initial points we are observing that Newton's method may not necessarily generate a sequence xk that converges to a root of gx is equal to 0. For a neat mathematical example of divergence of the Newton iterates, let me give you a home task that you take the function f(x) is equal to half of natural logarithm of 1 plus x square, and then show that for any x0 with modulus of x0 greater than equals to 1 upon root 3, the Newton's method generates a sequence xk that diverges. However, for any x0 with modulus of x0 less than 1 by root 3, the Newton method converges to a root of the equation f dash x is equal to 0, that is the point x is equal to 0, which is indeed the global minimum of the function f. I am keeping this observation as a home task. You please try to figure out why. Now question comes, for a general given function f that is just known to be twice continuously differentiable, is the Newton method having a local convergence property? The answer to this question is affirmative. Yes, Newton's method has local convergence property for any given function that is known to have continuous second order partial derivatives. Next, neatly we will show this local convergence property. We will in fact show that there is a region of attraction of the Newton method. Once Newton method is started from that region, then the subsequently generated points remain in that region and rapidly converges to or captures a local minimum with q order of convergence at least 2. Before getting into this local convergence result of Newton method, We need to recall a lemma from matrix analysis that states that we let capital A be a matrix valued function of p variables. That is, the matrix A gives us a matrix of order n by n for any given vector x in the p-dimensional Euclidean space Rp. And suppose this matrix valued function A is continuous at a point, say xi naught in Rp. Then we can show that if the matrix A xi naught is invertible, then for any given xi sufficiently close to xi naught, the matrix A xi is invertible and the function, the inverse of capital A, is continuous at the point xi naught. For a proof of this result, you may please visit the book by Chong and Jack that I have referred quite a few of times in the previous lectures. You please flip a few pages of Chong and Jack's book. You will find a proof of this result. I am not going to mention the specific page number from that book, which is one of the fundamental basic books for optimization. I strongly recommend my students, whosoever wishes to learn optimization, to start with the book by Chong and Jack. The book entitled An Introduction to Optimization by Chong and Jack is a very fundamental book for mathematical optimization. If you are inclined to learn mathematics behind optimization and you wishes to start your journey, then the book by Chong and Jack is a must pick up, and this book is not a reference book. This book is a textbook which is to be read back to back so that you will at the end of the day get enriched with mathematics behind optimization. Now next I will go for stating and proving the local convergence result of the Newton's method. And in the result we will see that Newton's method has q order of convergence at least 2, obviously under certain assumptions on the initial point. But you know, the superlinear convergence rate of the Newton's method is a bit trivial, and that is straightly followed from the derivation of the Newton method. Because you notice that in the Newton's method, we aim for finding a solution of 0 or null vector is equal to the gradient of the function. And suppose x bar is a solution to grad f is equal to the null vector, and from the Taylor's quadratic approximation of f around the current iterate xk, we see that this grad fx bar can be written as grad fxk plus the Hessian at xk times x bar minus xk plus small o of norm of xk minus x bar. Now if we pre-assume that this inverse of the Hessian at the point xk exists, and also suppose this sequence of the Hessian matrices is uniformly bounded with respect to a given matrix norm, that is, norm of this Hessian is bounded by a constant. Under these two assumptions, that this sequence is uniformly bounded and the Hessian is invertible, we go for pre-multiplying on both the sides by Hessian inverse. Then you will get this null vector is equal to the Hessian inverse times the gradient plus x bar minus xk plus the Hessian inverse times small o of norm xk minus x bar. So what we get here is that on the left, let me bring xk minus the Hessian inverse into grad fxk minus x bar, and let us keep on the right hand side the Hessian inverse times small o of norm xk minus x bar. Now on this left you have xk plus 1 minus x bar, and on the right you have the Hessian inverse times small o of norm xk minus x bar. Now if we take the assumption that this inverse of the Hessian matrices, that is this sequence, is uniformly bounded, that is across the points xk's you have norm of this matrix is bounded with respect to a matrix norm. Under this assumption, then we see that norm of xk plus 1 minus x bar divided by norm of xk minus x bar is less than equal to a bound, say capital M, of the norm of these sequences of Hessian times small o of norm xk minus x bar divided by norm xk minus x bar. We notice that this right hand side tends to 0 as k tends to infinity if we assume that the sequence xk is converging to x bar. So under these three assumptions, that the Newton sequence xk converges to a point x bar that satisfies this equal to 0. The second assumption, that these Hessian inverses are all existing and they are uniformly bounded. Under these three assumptions, we notice that this sequence xk generated by the Newton's method converges to x bar superlinearly. So superlinear convergence of the Newton's iterate is very evident. So Newton's method is obviously then faster than the steepest descent method. Steepest descent method is having only first order convergence rate. But here we see that from the derivation of the Newton's method, once the sequence xk converges to x bar, then it converges superlinearly. And not only this, under certain assumptions on the initial point and some assumptions on the Hessian matrix at a stationary point x bar, we can prove that the Newton's method converges to a stationary point with q order of convergence at least 2. The result neatly states that let the function f has continuous third order partial derivatives and x bar be a point such that the gradient of f vanishes at the point x bar, the Hessian matrix is continuous at x bar, and the Hessian matrix is also invertible at x bar. Then we can show that there exists a delta greater than 0 such that if the Newton's method is started at a point x naught inside the ball centering at x bar having radius delta, then each of the subsequent points or the entire Newton iterate sequence lies inside the ball Bx bar delta, and the sequence xk converges to x bar with Q convergence order at least 2. Now let us go for proving this result. In proving this result, we see that according to the hypothesis, the Hessian matrix is assumed to be continuous at x bar and it has inverse at the point x bar. So by this lemma that we have stated over here, let us name this lemma as lemma M, lemma for matrix, and thus the letter M is appended here. So by this lemma, we see that there exists a sufficiently close neighborhood of the point x bar in which the Hessian inverse exists and the Hessian inverse is continuous at the point x bar. So by this lemma, we have from the hypothesis of this theorem that by the assumptions of the theorem, that f has continuous third order partial derivatives and the inverse Hessian exists. The lemma M implies that there exists some delta bar greater than 0 such that the Hessian has inverse and continuous inside a closed ball having radius delta centering at x bar. Now as this Hessian inverse is continuous inside this compact set by Weierstrass extreme value theorem of continuous functions, this matrix function is bounded inside this closed ball, that is with respect to some matrix norm we have the inverse of the Hessian is less than equal to some constant m for every x inside this ball of radius delta bar. So we write here by extreme value theorem for continuous function, there exists some constant m such that we have this inequality is true. Now we go for the Taylor's expansion of gradient of f about the point x naught and get that the gradient of f at a point x that is nearby to the point x naught is equal to gradient of f at x naught plus the Hessian at x naught times x minus x naught plus big O of norm x minus x naught square. Here we will have big O because the function f is assumed to be having continuous third order partial derivatives. Now from this Taylor's expansion of gradient of f, we get that the norm of grad fx minus grad f x naught plus Hessian at x naught times x minus x naught. Sorry, here we will have minus. Its norm is less than equal to m dash times x minus x naught square of it for some m dash greater than 0. This inequality holds true for some neighborhood of the point x naught. Let's suppose in a delta dash neighborhood of the point x naught this inequality is true. Now take the minimum of delta dash and this delta bar and with this minimum of this delta dash and delta bar, this inequality holds true. Or without loss of generality, you just consider that the delta and delta dash for which this inequality as well as this inequality is true. So here, without loss of generality, we assume that this inequality is happening to be true inside the same ball. Now inside this inequality, we put x is equal to x bar, then we see that we will have the left hand side gives us this gradient of fx bar, that is an null vector. So this left hand side yields norm of gradient at x bar plus the Hessian at x naught times x bar minus x naught, that is less than equal to m dash times x bar minus x naught square of it. Now we bring out this Hessian matrix out of this norm, and the boundedness of this Hessian matrix inside this ball of radius delta bar gives us that the norm of Hessian at x naught inverse times gradient at x naught plus x bar minus x naught, its norm is less than equal to m into m dash times x bar minus x naught square of it, where this m is an upper bound of the norm of the inverse of the Hessian inside this ball, and therefore this left hand side yields x bar minus x1, that is given by x naught minus this entire expression, the full Newton step, and therefore this norm is less than equal to m times m dash into x bar minus x naught square. Now we define a new delta. We take delta to be minimum of this delta bar and some fraction divided by m times m dash for some alpha inside 0 to 1. Then in this delta neighborhood of x bar, you start your Newton iteration with the point x naught. That is, you take the initial point x naught to be inside this delta neighborhood of the point x bar, and then you go for employing this inequality and reach at this inequality, which further yields that if we take the initial point inside this delta neighborhood of x bar, we will get this norm of x bar minus x1 is less than equal to m dash into x bar minus x naught norm square, which further gives norm of x bar minus x1 is less than or equal to, as this norm of x bar minus x naught is less than delta. So we get here on the right hand side that m dash into alpha by m dash into x bar minus x naught, that is equal to alpha times norm x bar minus x naught, which is further less than alpha times delta, and as alpha is in between 0 and 1, this quantity is less than delta. So once this x naught is inside the delta neighborhood of x bar, the next iterative point x1 is also inside this ball of delta radius. Now subsequently, if we keep on employing that now x1 is inside this ball, then x2 will become inside this ball, and so on, we will get ultimately by induction that the entire sequence of iterates given by the Newton's method the sequence xk lies in the ball of radius delta centering at x bar, and also we have norm of xk plus 1 minus x bar is less than equal to m times m dash times xk minus x bar square, which comes from this inequality that once x naught is inside this ball, then you have this inequality, and further from here we get the norm xk plus 1 minus x bar is less than equal to alpha times norm xk minus x bar. This is due to this xk minus x bar has norm less than delta, and delta is less than alpha times 1 upon m dash. So we have this inequality true. Further from here you will have alpha into norm xk minus 1 minus x bar. So here alpha square. Keep on applying this inequality. We will end up with alpha to the power k plus 1 times the distance between the initial iterate and x bar. As alpha is in between 0 and 1, this tends to 0 as k tends to infinity. And therefore what we see that this sequence xk converges to x bar. And now from this inequality, the sequence xk converges to x bar with q order of convergence at least 2. So what we see here that the initial iterate x naught has to be inside this ball, and this ball is identified by taking up the radius delta as minimum of delta bar and this quantity, where this delta bar is the neighborhood of x bar in which this inverse of the Hessian is bounded, and this inverse of the Hessian exists. And accordingly, inside this delta neighborhood of the point x bar, all the inverse Hessian will exist. So the Newton iterates will be well defined, and ultimately we see that once x naught is started inside this ball, then the subsequent Newton iterates x1, x2, x3 and so on. In general, the entire sequence xk is lying inside this ball and converges to the center of this ball with q order of convergence at least 2. So the Newton method is quite fast, provided the assumptions of this theorem are holding, where these assumptions on this theorem are broadly on the initial point x naught. The point x naught has to be close enough to the stationary point x bar, and at this stationary point x bar, the Hessian should be continuous and the Hessian must have inverse. In addition, we have also assumed that the given objective function has continuous third order partial derivatives. But we notice that in the derivation of Newton's method, we started with a given objective function that has second order continuous partial derivatives. So you might think that this condition, third order continuous partial derivatives, might be an extra assumption we are taking off in this local convergence result. But you know, this local convergence result of Newton's method is also valid for a function that has second continuous partial derivatives. But for second continuous partial derivatives, we need to have some extra conditions that the Hessian matrix is Lipschitz in some neighborhood of the stationary point x bar. So I make a note here that instead of the function has continuous third order partial derivatives, you could also go with the function f has continuous second order partial derivatives and the Hessian is Lipschitz in some neighborhood of the point x bar. For a neat statement of local convergence of Newton's method with second order continuous partial derivatives and Hessian is Lipschitz, you may please visit the proposition 1.4.1 on page 97 of a classic book on optimization by Bartesekas entitled Nonlinear Programming in its third edition, which was published through Athena Scientific in the year of 2016. In this book, at the proposition 1.4.1, you will find a local convergence of Newton's method with Q convergence order at least 2, where instead of these continuous third order partial derivatives, we go with continuous second order partial derivatives together with an extra condition that the Hessian matrix is Lipschitz. So neatly from the discussion of the Newton's method so far, what we get is that Newton's method is a fast method having a Q convergence order at least 2, provided the initial point is sufficiently close to a stationary point x bar. And in general, Newton's method is not globally convergent. Now question comes, can we devise a method for which this fast convergence rate of the Newton's method can be used, as well as the global convergence of first order optimization techniques can also be used? Yes, there are some global convergent modification of Newton's method, and the basic idea behind framing this globally convergent modification of Newton's method is to combine a globally convergent strategy like in steepest descent method with a fast locally convergent strategy like for Newton's method, combining a globally convergent strategy with a locally convergent fast strategy, we get a hybrid method that goes globally convergent. Such a modification of Newton's method are available in the literature, and the basic idea behind this hybrid method is that it enjoys the benefits of both global convergence of first order methods and local fast convergence of Newton's method. Towards this globally convergent modification of Newton's method, a possible basic idea is that you start from any initial point x naught from the n-dimensional Euclidean space and keep on employing the steepest descent direction as long as the iterative points are not close to a solution of grad f is equal to 0. That means as long as gradient at xk has norm bigger than a threshold, then you keep employing the steepest descent direction. At x naught, you employ the steepest descent direction. You reach at the point x1. Then at x1 again you employ the steepest descent direction. You reach at x2. Check at x2 whether the gradient has norm greater than tau or not. If greater than tau, then again employ the steepest descent direction and keep on employing steepest descent direction as long as this norm is greater than tau. But when norm is less than a threshold value, then we can pre-assume that we are reaching close to a stationary point of grad f is equal to 0. When we are reaching very close to a stationary point, we know the steepest descent method is very slow. So once we have reached to a close neighborhood of a stationary point, what we can do? As we have reached very close to a stationary point, say x bar, then what we do that instead of employing steepest descent direction, we go for employing now Newton's direction, and you will then fastly reach to a stationary point. So initially you start with steepest descent direction and then switch over to the Newton's direction once you have reached near to a stationary point. So this could be a possible globally convergent modification of Newton method. For an elegant reference of different variations of Newton methods and several globally convergent modification of Newton's method, I would suggest you to follow a book entitled Newton Types Method for Optimization and Variational Problems by Izmailov and Solodov, which came out through Spinger in the year of 2014. Here I mention neatly this globally convergent modification of the Newton method. As I have mentioned that keep using the steepest descent method, replacing Newton direction when the norm of the gradient is large, greater than a threshold, and when this gradient is less than the threshold, then we can expect having reached in a sufficiently close region of a solution to grad f is equal to null vector. So we start using the Newton step. And by using the Newton step, we can firstly reach at a stationary point of the function f. Now I will end up this lecture by mentioning Levenberg-Marquardt modification of Newton's method when the Hessian matrix might not be positive definite. So far we have been thinking that the Hessian matrix is positive definite and hence the Newton direction is a descent direction. But in case the Hessian matrix is not positive definite, what is a possible way out? That is answered in the Levenberg-Marquardt modification. The Levenberg-Marquardt modification is as follows. That we consider the Hessian matrix that might not be positive definite, but as the Hessian matrix at the point xk is a symmetric matrix, its all eigenvalues are real and suppose for this Hessian matrix at the point xk the eigenvalues are lambda 1k, lambda 2k till lambda nk. As this matrix Hxk is not a positive definite matrix, so all these eigenvalues are not all positive, but if we add a sufficiently large quantity to each of these eigenvalues, let us go for adding mu k to each of these eigenvalues, then we see that for sufficiently large value of mu k, all these values lambda 1k plus mu k, lambda 2k plus mu k till lambda nk plus mu k are all positive, and we note that these values lambda 1k plus mu k till lambda nk plus mu k are eigenvalues of the matrix Hxk plus the identity matrix of order n. This n is the number of variables of the function f, and hence this Hessian matrix is of order n by n. So we observe here that this matrix Hxk plus mu k in has eigenvalues lambda 1k plus mu k, lambda 2k plus mu k till lambda nk plus mu k. It is a simple exercise to prove that if lambda 1k, lambda 2k, lambda nk are eigenvalues of this matrix Hxk, then these n quantities are eigenvalues of this matrix Hxk plus mu k times in. As all these n quantities are positive, So this matrix is a positive definite matrix. As this hxk plus mu k in is positive definite, it has an inverse, that is hxk plus mu k in inverse exists, and hence hxk plus mu k in inverse times negative of the gradient is a descent direction of f at xk. Since once this matrix is positive definite, its inverse is also positive definite, and a positive definite multiplication to the negative of the gradient is evidently a descent direction. Once you have found a descent direction, that is a modification of the Newton's direction hxk inverse times grad fxk, then you go for employing this direction, which we shall refer as Levenberg-Marquardt direction, or we shall denote by DKLM. LM stands for Levenberg-Marquardt, and with this DKLM you keep on identifying the iterative points from x0. You go along this direction denote LM, then reach at the point x1. You may take a suitable step length along this direction alpha naught. So x1 is given by x naught plus alpha naught times this d naught Lm. Reaching at x1, you check whether the gradient has norm less than a threshold or a tolerance level epsilon or not. If not, then go for again employing the descent direction d1 Lm and compute the next iterative point x2 and so on. Keep computing as long as you are not getting a point xk at which the norm of the gradient is less than epsilon. So this is the Levenberg-Marquardt modification of the Newton's method. Now here we notice that this mu k value gets changed across the iterations. A rule of thumb for choosing this mu k, that you consider the negative of the negative most eigenvalue as mu k, and you add this mu k at all the eigenvalues, you will get all the eigenvalues non-negative. So for a rule of thumb, you choose mu k is, you choose 0, that you don't add anything if all eigenvalues lambda ik are positive, or you consider negative of the minimum most eigenvalues lambda ik's over I is equal to 1 to n. You add with this negative of the minimum most eigenvalue some small quantity epsilon k, a positive quantity, and then we'll see that by considering this expression for mu k, by adding this mu k on this matrix hxk, consider hxk plus mu k times in, we see that this hxk plus mu k times in is positive definite, and then with this matrix you can go for employing the Newton's method. Notice that in the case when mu k, we choose mu k so that mu k is very close to 0, then in that case this Levenberg-Marquardt modification of the Newton's direction approach to the behavior of the Newton's method. On the other hand, if we consider mu k very large, ideally mu k tends to infinity, then we notice that this diagonal matrix mu k times in is going to dominate the entire matrix hxk plus mu k times in, dominates in the sense of all the eigenvalues of this hxk plus mu k times in are almost going to be mu k, and therefore when mu k tends to infinity, you notice that this Levenberg-Marquardt direction approaches to the direction of negative gradient, and hence when mu k tends to infinity, this Levenberg-Marquardt modification reduces to the steepest descent method. So if you take mu k very large, Levenberg-Marquardt method is going to be very slow because steepest descent method has a very low rate of convergence. But for very small value of mu k, this matrix hxk plus mu k in is going to be ill conditioned. By ill conditioned, I mean the condition number of this matrix is going to be very high. The condition number of a positive definite matrix is defined by the maximum eigenvalue of the matrix divided by the minimum eigenvalue of the matrix. If a matrix capital A has high condition number, then we call the matrix A ill conditioned. For a given ill conditioned matrix, a small perturbation of the entries of the matrix A will lead to have huge fluctuations in the solution vector x for a system of linear equations Ax is equal to b. And in finding this Levenberg-Marquardt descent direction, we commonly do not consider to employ the inverse. We in fact use the Cholesky factorization scheme that I have described earlier to find this DKLM. So we require to solve a system of linear equations in which this matrix is having high condition number if this mu k is very high, and therefore it is suggested that you take a value of mu k, a moderate value, so that it is not very small and not so high. Commonly what you can do here, instead of considering this epsilon k, you can just go for adding a value, say simply the unity, and then go with this mu k with this expression. That would commonly work well. Or in practice what we can do, that you take a small value of mu k at the beginning of the iterations and then slowly increase the value of mu k unless we find that this direction DKLM is a descent direction. So here I neatly write here this comment that as mu k tends to 0, the Levenberg-Marquardt direction is almost the Newton's direction, and when mu k tends to infinity, the Levenberg-Marquardt direction is almost steepest descent direction. Now next I will consider two examples. In the first, I will employ damped Newton method with the step length alpha k to be chosen with one of the inexact line search methods. Say, let me consider the Armijo backtracking. And in the next example, I will consider the Levenberg-Marquardt method to be explored. So in the first example, let me now consider to explore numerically Newton's method with inexact line search. For example, I will consider here the Armijo backtracking rule. Here, not exactly the Newton method, the damped Newton method will be explored. We consider the test function, the Rosenbrook's function. One of the test functions, the Rosenbrook's function, that is used to check efficiency of an optimization algorithm, whose expression is given by, which is a function of two variables, f(x1), x2 is equal to 100 times x2 minus x1 square of it plus 1 minus x1 square. This function is also known as a banana function because the shape of its level curve, I have shown in one of the previous lectures that this Rosenbrook function is having a banana shaped level curves. There are several kinds of test functions having several peculiar features, which functions are used to check the efficiency of an optimization algorithm. In this era of internet and openly available resources, You can easily find some other test functions. You just Google up, you will get some test functions. Those are commonly used to check efficiency of optimization algorithms. As I do not have any unique reference for test functions, I am not going to refer any of the references. So I would request you please search over the internet, and from the openly available resources you can figure out quite a few test functions. Those are used to check efficiency of optimization algorithms. Now here I will consider the test function, the Rosenbrook's function, to explore the damped Newton's method with inexact line search. You go for taking the initial point as the null vector, and in the Armijo backtracking rule you consider the value of C1 is equal to 1/4. For the backtracking, the constant factor tau is, let's suppose, half, and the initial estimate of the step length that is to be used in backtracking is, let's suppose, 1. And also go with the tolerance level or the precision level, epsilon is equal to say 0.01. With these parameter values, let us now go for computing two iterations of the damped Newton scheme. In order to execute the next iterative point, we need to find the Newton's direction at the point x0. To find Newton directions across the iterations, let me consider first to write out the gradient and Hessian at general points. The gradient at x1, x2 is given by 400 times x1 cube minus 400 times x1 x2 plus 2x1 minus 2, and the second component is 200 times x2 minus x1 square, and the Hessian matrix at the general point x1 x2 is given by this 2 by 2 matrix. Inverse of this Hessian when exists is given by 1 over this expression times this 2 by 2 matrix. Now we are ready to compute the next iterative point x1. We see that x1 is given by, in the damped Newton scheme, x naught minus a step length alpha naught times the Hessian inverse times the gradient at the point x naught, where this alpha naught is given by the Armijo backtracking rule. The Armijo backtracking rule for this Newton direction d naught which gives us the vector, you please compute the vector 1 0, is given by this inequality. You employ the backtracking rule starting with alpha bar is equal to 1. Keep on reducing this alpha bar by the factor tau and check for which value of the factor t to the power p times alpha bar satisfies this inequality. You notice that this Armijo rules inequality gives us the restriction of alpha given by, you please cross check, 100 times alpha to the power 4 minus 3 alpha by 2 plus alpha square less than 0. Now you go for employing the backtracking To identify the step length alpha naught, we start with alpha bar is equal to 1 and check if this inequality is true. We'll see that this inequality 1 is not true. For alpha bar is equal to 1, now you reduce this alpha bar by the tau factor. You consider tau times alpha bar, which is equal to half. You will see that for alpha is equal to half, the inequality 1 is still not valid. Go reducing a bit more, t square alpha bar, which gives us 1/4. For alpha equals to 1/4, you will see that this inequality is still not valid. But for another reduction, t cube alpha bar, which is equal to 1/8, will give us that the inequality 1 is true. So this alpha naught is given by 1/8, which is found by the inexact line search method, the Armijo backtracking rule. So this x1 is given by x naught, which is the null vector, and minus times alpha naught 1/8 times -1 and 0, which ultimately gives us 1/8 0, and that is the next iterative point. Now you check the norm of the gradient at the point x1. You compute it and check if this is less than epsilon, the tolerance level. If not, then go for the next iteration, iteration number 2. I am keeping the iteration number 2 to compute x2 as a home task. To find x2, you repeat this entire process, replacing this x naught by x1. You will find the value of x2. Now next I will show one example where two iterations of Levenberg-Marquardt modification of the Newton method will be executed. Apply two iterations of the Levenberg-Marquardt method, or we do write pure Levenberg-Marquardt method with the initial point 0, 3 and termination scalar or the tolerance level epsilon is equal to say 0.01 on the function if x1 x2 is equal to x1 minus 2 to the power 4 plus x1 minus 2x2 square. By here this pure Levenberg-Marquardt method, we mean the Levenberg-Marquardt method with the step length is equal to 1. Like in pure Newton method, we consider the step length to be 1. Similarly, in pure Levenberg method, we will consider the step length to be is equal to the constant step length 1. To find the iterative points by the Levenberg-Marquardt method, we first find the expression of gradient and Hessian at a general point x1 x2. The gradient is given by 4 times x1 minus 2 to the power 3 plus 2 times x1 minus 2x2. The second component is minus 4 times x1 minus 2x2. The Hessian matrix at x1 x2 is given by these 2 by 2 matrix. Now we go for computing the iterative points. In the first iteration, we have x naught is equal to 0, 3. The gradient at x naught is the vector, if we cross check, minus 44 and 24. The Hessian matrix at x naught is This matrix, now you consider the value of mu naught is equal to, by the rule of thumb, or you can just go for adding the trace of this matrix. You consider, let's suppose, 58, and then the modified Hessian in the Levenberg-Marquardt method is this matrix, which is equal to this 2 by 2 matrix, and hence the Levenberg-Marquardt descent direction is given by this inverse times the gradient at x naught. You compute what is this d naught lm, and then the next iterative point x1 is given by x naught plus unit step length times d naught lm, which is given by the vector 0 3 minus 1 divided by 7 1 1 2 times this matrix into the vector this one. You please compute what is this vector x1. After computing x1, please check the gradient is having norm less than epsilon or not. If yes, then stop and give the output x1 as a stationary point of the problem. And if this inequality less than epsilon is not valid, then go for computing the next iterative point. I am keeping this as a home task. With this quite a few home tasks, I stop this lecture here. In the next lecture, our topic of discussion will be exclusively the quasi-Newton methods. Now, I put a sincere thanks, my heartfelt thanks to all of you for your kind attention. Thank you all.